Hi, hello everyone. This is the educator, your tutor, your friend Sanjay Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. Do watch this session. If you like it, do press the like button and share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Alright. Do visit our website also www.v-learning.in. You will be getting all these sessions there. Along with that, you will be getting lecture notes also for each and every lecture. You can download it, you can use it, you can read them again and again. Alright, it will be very useful for you. Okay. Now, without any delay, let's get started with the session. So we were doing current electricity and this is lecture number 6. In this lecture, we'll be talking about combination of resistors part 1, where we'll be seeing series combination, parallel combination and Wheatstone bridge. Now, this is something which you have already done in your 10th standard. Series combination, you already know what it is, right? Parallel combination, you already know what it is. So it will be a kind of revision for you. Wheatstone bridge is something which will be new for you. Alright, so take out your notebooks and pens and we'll start. Let us start with the revision of what you already know. Combination of resistors. So now, first is series combination. When do we call that two resistors are in series? When the tail of the first resistor is connected to the head of the second resistor directly and there is no other connection between them. Right? If you see this particular combination, here, this is a resistor. The tail of this resistor is connected to the head of this resistor. Let's say this side is head, this is tails, this is head, this is tail, this is head, this is tail. Not head and tails of coin. Head means head, tail means tail. Okay. So now this tail is connected to this head. This tail is connected to this head directly. There is no other resistor or there is no other thing. If it is like this, then we will not call them as series. We'll only call them as series when there will be no connection between the tail of this and head of this. Clear? I hope you are getting the point. Alright. So now this is a series connection. Let's say this is resistor R1. This is resistor R2. This is resistor R3. Let's say the voltage supplied by battery is V. Now, in series, first thing, what remains same and what gets distributed? Now, since it is one complete circuit, right? What will be same? The current will be same. Alright. The current, whatever current will be drawn from the battery, let's say it is I. The same current will be going through this resistor, the same current will be going through this resistor, and the same current will be passing through this resistor, and the same current will come back to the battery. Clear? So in series, current in all the resistors remains same. What gets distributed is voltage. The potential difference across this resistance will be different, across this resistance will be different, and across this resistance will be different. Clear? Now if I ask you what is the potential difference across this particular resistor R1, if I connect a voltmeter, how much potential will it show? It will be, what is potential difference? If a current I is passing through a resistor and the resistance is R, what will be the potential difference? I into R. Correct? So here R1 is there, current is I, so potential difference will be IR1. IR1. Alright. Here it will be IR2. Here it will be IR3. Or before writing here IR1, IR2, I'll write V1, V2, V3. V1, V2, V3. The potential is distributed as V1, V2 and V3. Okay. Now, how do we find the equivalent resistance in this circuit? What does equivalent resistance means? There are three different resistances. I want only one resistance. If I could replace all the three resistance with only one resistance, and the value of that resistance should be such that the current from this V volt battery should be I only in the entire circuit. Okay, let us make an equivalent circuit. What I told, I want an equivalent circuit where In this circuit, there will be only one resistance. The battery will be of voltage V only. There will be one resistance which I have placed in place of all these three. Okay. Now, by putting this particular resistance, the current drawn from the battery should be I. So what will be the value of this resistance? Or what will be the equivalent of all these three resistors? Okay, let us find out. From here, if I ask you what will be the potential drop across this, if I current is there, V is equal to I R equivalent. Correct? V is equal to I R equivalent. From here, if I want to write for V, what we can write? V is equal to V1 plus V2 plus V3. Correct? Total potential. From here I can write V is equal to IR equivalent. From here V is equal to V1 plus V2 plus V3. This we already know that how much ever voltage will be distributed here, the sum of all these three voltage will be equal to the battery, because that is the potential difference what battery is providing. Correct? So total potential will be V1 plus V2 plus V3. Now V is equal to V1 plus V2 plus V3. What is V1? Potential difference across R1. Current is I, resistance is R1. It will be I R1. Are yes or no? Plus across R2. V2 is across R2. Current is I, resistance is R2. I R2. V3 across R3, right? I R3. So from here, now what is V? I R equivalent. Right? So from here I can write this is I R equivalent. Now see here, I R equivalent is equal to I, if I take common, this will be R1 plus R2 plus R3. Now this I will be cancelled. What I am left with, R equivalent is equal to R1 plus R2 plus R3. This is the equivalent resistance when three resistances are connected in series. Alright, that means a resistor whose resistance is equal to the sum of all these three resistors. If I connect that resistor here, removing all these three, if I connect a resistor whose resistance is equal to the sum of all these three, then also the current in the circuit will be I ampere only, if the battery is of V voltage. Clear? This is R equivalent. So first thing what you have to remember, in series the current in all the resistors is same. The potential difference gets divided. Now how this potential difference gets divided? R equivalent, you know this. Potential gets divided. Potential is shared among all the resistors in the ratio. What will be the ratio? V1 is to V2 is to V3, and that is equal to R1 is to R2 is to R3. Clear? R1 is to R2 is to R3. And if I talk about how much will be the current in the circuit, how much will be the current in the circuit? I, that is equal to V upon R equivalent, total potential supplied by the battery, divided by the equivalent resistance. So this will be V upon R1 plus R2 plus R3. And that is equal to, see here, if the potential difference is V1, and the resistance is R1, what will be the current? V1 by R1, right? That is I only. So this will be equal to V1 by R1. That is equal to V2 by R2. And that is equal to V3 by R3. Correct? See here, this is R1. Alright. Now if you take the ratio of this, V1 is to V2 is to V3 will be R1 is to R2 is to R3. Okay. That's what we got here. Done. I hope you got the current, you got how the voltage is distributed, and this is the equivalent resistance. These are the three main things, three main conclusions. Now, next, parallel combination. What is parallel combination? This is parallel combination, where this resistor, can you see this? This is the battery with voltage V, this is R1, this is R2, this is R3. The head of one resistor is connected to the head of the other. The tail of one resistor is connected to the tail of the other. This is the head, this is the tail. This is the head, this is the tail. This is the head, this is the tail. Here the head of this is directly connected to the head of this. The tail of this is directly connected to the tail of this. Here again the head of this is directly connected to the head of this. The tail of this is directly connected to the tail of this. Here also the head of this is directly connected to the head of this, and the tail of this is directly connected to the tail of this. These two are in parallel, these two are in parallel, these two are in parallel. Even all the three are in parallel. Clear? All the three are in parallel. So in series the head is connected to the tail directly. In parallel, head to head and tail to tail. Clear? Head to head and tail to tail. Now, so in series we have seen current remains same, potential gets distributed. Here, see, this is the battery. This is plus, this is minus. So this will be basically V, plus minus means this is higher potential, this is lower potential. Or we can say this is at V, this is at 0. Just for our understanding. So that means this point is at V, this point is at also 0. See, this is at V, that means this point is at V, this point is at 0. From here to here there is no resistor in the middle, so there will be no drop of potential, so this will be V. Here also there is no resistor in the middle, there will be no drop or gain, so this will also be at 0. From here to here again on the way there is no resistor, no electrical component, so there will be no potential drop. So this point will also be at V, this point will be at 0, because from here to here also it's a plain wire. From here to here again this will be at V and this point will be at 0. Now see, this resistor across this, the potential difference is V minus 0, that is V. Across this also V minus 0, that is V. Across this also V minus 0, that is V. Potential difference across all the resistors is same. Clear? In parallel, potential difference across all the resistors will be same, that is V, V and V. Clear? If you want, you can note down. What is distributed here? Current. See, the current I, let's say I current is drawn from the battery. This I will go here. Then the moment this I reaches here, there are two different roads it has to travel. So what it will do, it will distribute itself. I1 will go here, I2 will go here. Clear? So now I2 is going here. Again here, if you see, it will be distributed. Two currents. So let's think this way. So in all the three resistors, basically three different currents will go. In all the three resistors, three different current will go. Let's say here I1 is going, here I2 is going, here I3 is going. Okay. So from here I1 will come, from here I2 will come, from here, see, here I1, from here I2 is coming, and I1, I2 got mixed here. Then from here I3 is coming, I1, I2 is coming from here, I1, I2, I3 got mixed here. So ultimately I current is going inside. I current is drawn, it is distributed in three different currents, I1, I2, I3. I1 is going here, I2 is going here, I3 is going here. While coming back, here I1 is coming, here I2 is coming, here I3 is coming. Again, if you see, this will be I1 plus I2. Because from here I1 came, from here I2 came, they joined together, I1 plus I2. From here I1 plus I2, I3, all these three will join together, I1 plus I2 plus I3. Total current is I1 plus I2 plus I3, that is I. So basically I current is coming back. Clear? Or basically I current is coming back. Okay, I was the one which was distributed in I1, I2 and I3. So basically I1 plus I2 plus I3 is what? I. Simple. So from here I can write I is equal to I1 plus I2 plus I3. Now I want an equivalent resistance for this entire circuit. What does that mean? I want a resistance, I want a resistor whose resistance will be such that I can replace all these three resistors with that one resistor, so that the potential difference across is maintained as V and the current will be I, the total current drawn from the battery. Okay, so here the equivalent resistance will be something like this. Current should be I. From here I can write V is equal to I into R equivalent. Or let's say from here I can write I is equal to V upon R equivalent, correct? See, now there is a way to derive. There, voltage was distributed, so we derived by the equation V is equal to V1 plus V2 plus V3. Here current is distributed, so we are going to derive from I is equal to I1 plus I2 plus I3. Whatever is distributed, that thing we will make, we'll do the sum of that and we'll derive from there. Clear? So now I is equal to V upon R equivalent. What is I1? From here, potential difference is V, that is anyways provided by the battery. Current is I1, resistor is R1. What will be the current I1? V by R1, correct? So this will be V by R1. What will be I2? Resistor is R2, potential difference is V. So V by R2. What will be I3? Resistor is R3, potential difference is V. V by R3. From here if you see, this V is cancelled. What we are left with is 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. This is the equivalent resistance when the resistors are connected in parallel. So we will solve this. From there we will get 1 upon some value, or we will get a fraction. If I solve this, we will get a fraction. The reciprocal of that fraction will be R equivalent. Don't be mistaken. Some people, they think, oh, this is R equivalent. They will solve this, whatever value will come, they will write as R equivalent. No. This is 1 upon R equivalent. Solve this, you will get a fraction. Reciprocal of that fraction will be R equivalent. Clear? Alright. Now, from here, if I want to write current will be shared in which ratio? Current will be shared in all the resistors in the ratio I1 is to I2 is to I3, correct? That is equal to 1 upon R1 is to 1 upon R2 is to 1 upon R3. In this particular ratio, the current will be distributed. Clear? Note it down. And what will be the voltage? Potential difference across each resistor. V is equal to I into R equivalent, right? So that is 1 upon R1 plus 1 upon R2 plus 1 upon R3. 1 second. Wait. I into R equivalent. R equivalent is 1 upon R1, 1 upon R2, 1 upon R3, correct? Or we can write as V is equal to I1 R1. Are yes or no? That is equal to I2 R2. That is equal to I3 R3. From here, V is equal to I1 R1, V is equal to I2 R2, V is equal to I3 R3. Alright. So from here what we can understand is the resistor which is having the smallest value will draw the maximum current. Because we have to keep them equal, right? The resistor having the smallest value will draw the maximum current. And now there is one more conclusion what we can get from here. From this, or let me show you from here, series. R equivalent is the sum of all the resistors. That means whenever the resistors are in series, the equivalent resistor will be having the resistance more than the highest resistance. Equivalent resistance will be more than the highest individual resistance. Correct? Because it is basically the sum of all. Let's say the highest is R1. Let's say there are 3 resistance. This is 10, this is 5, this is 2. This is the highest. R equivalent will be the sum of all. That will be anyways more than 10. 10 plus 5, 15 plus 2, 17. So this is always true. In series, R equivalent will be more than the highest individual resistance connected in series. And in parallel, R equivalent will be less than the smallest individual resistance. If you want, you can note it down. R equivalent will be less than the smallest individual resistance connected in parallel. So if you remember this, it will help you in rechecking your answer. Suppose you have done some calculation like this. Now your R equivalent came bigger than some value, bigger than let's say the smallest resistance. That means your calculation is wrong. It has to come smaller than the smallest individual resistance which is connected in parallel. Clear? Got it? Now, let's go further. Find the current passing through battery. So now this is a question where series and parallel both are mixed. Okay, why directly I came up with this question? Because this is anyways a kind of revision. You have already done these questions in your 10th standard, right? How to solve this? Very simple. I can resolve this circuit. These 3 are in parallel. So if I solve for these 3 parallel, I'll get an equivalent resistance here. This is a battery and one resistance is here. So this will be 30 volt. Now what will be, this is 1 ohm. What will be the equivalent resistance which will come here? 1 upon R dash is equal to, let's say this is R dash, okay? 1 upon R dash is equal to 1 upon 2 plus 1 upon 3 plus 1 upon 6. Now, to make this denominator as 6, what will be the LCM of these 3? 6. To make this denominator as 6, what I'll do? I'll multiply 3 both up and down. So this will become 6. Here it will be 3. To make this as 6, what I'll do? I'll multiply both 2 up and down, right? So 3 by 6, 2 by 6, 1 by 6, 3, 4, 5, 6, 6 by 6. That is 1. 1 upon R dash is 1. So R dash will also be reciprocal of 1, that is 1. So that R dash will be R dash will be, I don't think there is a need to show this, or I'll show, not a problem. 1 upon R dash is equal to 1 upon 2 plus 1 upon 3 plus 1 upon 6. So R dash is equal to 1 ohm. So here also R dash is equal to 1 ohm. If you solve this entire thing, these two are connected in series. See, the tail of this is connected to the head of this, right? So now these two are in series. So R equivalent will be the sum of this plus this. 1 plus 1 is 2. So finally you can write R equivalent is equal to 1 plus 1, that is equal to 2. Question is, find the current. I is equal to total potential upon R equivalent. Correct? That is equal to 30 upon 2, that is 15 ampere. I hope you got the same. Total potential difference upon total equivalent resistance. Clear? That will be the current from here. Or for some people, let me make it more simpler. See, these two are in series, so equivalent will be 2 ohm. Let me make a circuit here. So basically, it is given like this. 1 ohm, 1 ohm. This is 30 volt. Making equivalent circuit for this, it will be 2 ohm. This is 30 volt. Current is I. Now can you solve this? Right? See, these two are in series. The sum is 2. Current is equal to, I is equal to 30 upon 2, that is equal to 15 ampere. So 15 ampere current will be drawn from here. Clear? Easy question. Alright. Next, find the equivalent resistance in the following circuit. Try this on your own. Again, it is easy. A mix of series and parallel. That's all. How do we do this? Whenever you get a question like this, just see which all are in series. First solve the smallest, go deep inside and see. Solve the series, solve the parallel, then again you will get one more series parallel, then keep on solving one by one. Okay. First, if you see this resistance, is it parallel to this? No. The tail is not connected directly to the head because there is two more wires here. This also, is it connected parallelly to this? Yes. This and this are parallel. See here, this is one point. This tail is connected to, or let's say this head is connected to this head. This tail is connected to this tail. Correct? Now, if here there is no other resistor, this is basically a short circuit, a direct wire is connected, I can make this point near to it. If I bring this point near to it, this resistance will become like this, the same 3 ohm. I am just shifting this point. So these two are in parallel. Now before solving this parallel thing, what you can solve is this one. See, these two are in series, 2 ohm and 1 ohm. The tail of this is connected to the head of this directly. There is no other wire in the middle. Correct? So from here, if I make an equivalent circuit, this will be 8 ohm. Then these two, if I join together, it will be 2 plus 1, 3. Series, right? They will add up, 3. So now from here there is a 3 ohm. Here also there is a 3 ohm. And as I told, this point and this point are same points. Correct? I can join them. So this will be like this. Now see this one, 2 and 1 will become 3. One more resistor will come here, that is 3 ohm. Correct? Now one side of this 3 ohm and other side, these two will join and become 3 ohm, other side is connected here. That means this point, if you see, if I take this as point A, this point is B point, this point is also B point. Correct? And this is connected to B. This is connected to A, this is connected to B, this is connected to A, this is also connected to B, this is connected to A. All these three resistors, if you see across them, the potential difference is VA minus BB. One point is A, other point is B. For this also one point is A, other point is B. For this also, the series combination also, one point is A, other point is B. All the three are in parallel. These three are in parallel basically. Correct? If this wire I have made like this, if I instead of making like this, I can make this way also, see. Correct? Now can you understand these three are in parallel? Now these three are in parallel. I can solve these three and make one equivalent resistance between A and B. If this point is A, this point is B, between A and B I can make one equivalent resistance. What will be that one? It will be 1 ohm. How? If, now remember this also. If equal resistances are connected in parallel, the equivalent resistance will be the value of that one individual resistance divided by the number of resistance. So value of one individual is 3, divided by number of resistances which are connected in parallel, that is 3. 3 by 3 is 1 ohm. The equivalent will be 1 ohm. Okay? Keep this in mind. You can solve and see also. See, if I take the equivalent as R dash, so 1 upon R dash will be equal to 1 upon 3 plus 1 upon 3 plus 1 upon 3. These three are in parallel, right? 1 upon 3 plus 1 upon 3 plus 1 upon 3. So this will come as 3 upon 3. That is 1 upon 1. Reciprocal of it will be R dash, that is 1. See, 1 ohm has come. Okay? So remember, if equal resistances are connected in parallel, the equivalent resistance will be the value of one individual resistance divided by the number of resistors. Clear? So this R dash will be 1 ohm. So here 8, this will become 1 ohm. And this is one battery connected. How much is that battery? Oh, they have only asked equivalent. They did not ask current and all, so there is no need for the potential difference. From here, these two are in series. Series means sum. Sum means this will be 8 plus 1, 9. So there will be the battery. This is 9 ohm. Clear? This battery I have made like this. This is 9 ohm. R equivalent is equal to 9. What the point? Easy. Practice more. They are easy questions. Next, Wheatstone bridge type combination. Now this is something which is new for you. You haven't studied this in your 10th standard. Okay. What is Wheatstone bridge type combination? Here you will see a circuit like this, where one point will be A, one point will be B. Okay. One resistor will be connected like this. There will be another resistor, but between these two resistors there will be one more resistor. From here, the same A point, there will be one resistor like this. From this, there will be one resistor, but before that there will be one resistor which will be connected like this. So this kind of combination is known as Wheatstone bridge type combination. Okay? Just see it properly. Point A, point B. From A, two resistance are coming out. From B also there are two resistance, and in between there is one resistance. This is Wheatstone bridge. Okay? Looks like a bridge only. Fine. Now, if here there is one result which you have to remember always, that will help you a lot. We'll prove that result also, don't worry. If R1, one second. Okay, I'll write here. If R1 by R3 is equal to R2 by R4, the ratio of these two resistors is equal to the ratio of these two resistors, R1, R3. Don't remember the numbers, only remember the arms. These two which are coming from A, from this point, the ratio of these two and which are joining here at B, the ratio of these two is equal. You can take the ratio of these two also, because see, R2 can come here, R3 can go here. So the ratio of these two is equal to the ratio of these two. Anything, but I prefer learn it in this way. From this one side ratio and one side ratio, if they are equal, what does this mean? This means that this point and this point, let's say this is X, this is Y. This point is A, this point is B. I'm assuming this point is at potential X, this point is at potential Y. Okay? X and Y are at same potential. Very, very, very important result. Note it down. If R1 by R3 is equal to R2 by R4, that means X and Y are at equal potential, are at same potential. What does this mean, same potential? If 2 points are at same potential, that means current do not flow in those among these 2 points. Current will not flow from here to here. Current only flows when there is a potential difference. Correct? This ball, let's say, I'll take you to very basic. This ball is here. It will automatically fall from here to here, right? You don't have to do anything. Why? Because there is a difference in height. But now, if I keep this ball on this ground like this and I don't push it, I'm not doing anything. Will this ball start moving? It won't. There is no difference in height. The same way we have studied in potential basics of electricity when we were doing, current only flows from higher potential to lower potential. When there will be a potential difference, current will flow. These two are at same potential, the current will not flow here. The current will not go through R5. What does this mean? I can remove this wire. It is useless. This wire is useless. The current is going from here and here. That means, see here, the current is going, let's say I1 and I2, it gets distributed. Let's say that it is connected to a battery. Okay. This is potential A, this is B, so this is at point A, this is point B. So now current is coming from here, current I is coming, and this I is distributed in I1 and I2. Current is not flowing in this. What does this mean? When I1 is going here, it is going here, same I1 is going here, because it is no current is going here. Nothing is going here. So whatever current was coming from here, the same current is going here. I1. So if the same current is going there, we know that when two resistances are in series, the current in them is same. Here, in both these resistances, the current is same. Here also this I2 will go here, nothing will go here, right? Because the current is not flowing here. Both are at same potential X and Y. So this I2 will only go here. Ultimately, this I1, I2 will join here and come out as I, and the same current, it will go here, right? I should connect this to this B. This will come out here and go as I, right? So if same current is going in these two resistances, that means these two resistances are in series. These two resistances are in series. And when two resistance can be in series? When the tail of this is directly connected to the head of this, that means there is no other wire in the middle. I can actually remove this wire. Finally, our combination will look like this. Clear? Current I1 is going here, the same I1 will flow here. I2 is going here, the same I2 will flow here. We can remove this wire because this point and this point are at same potential. Now can you solve this question? Earlier at first when you would have seen this and I would have asked you to solve this, it would be very difficult because neither these two are in series, nor these two are in series, nor these three are in parallel, nor these three are in parallel. There is no series or parallel what we can get to know from here. You can never get to know, right? But just because these two are equipotential, I can remove this wire. Now see, this question can be solved easily. These two are in series, I will solve them. These two are in series, I will solve them. So this arm and this arm will be parallel. I will solve these two arms, I will get one equivalent resistance. Got the point? So this condition is known as balanced Wheatstone bridge. Balanced Wheatstone bridge. We can only remove this wire from the middle if the Wheatstone bridge is balanced. Okay? When it will be balanced? When R1 by R3 will be equal to R2 by R4. Now let us prove this. That when this is there, X and Y are at same potential, we'll prove it. Okay? So this is the same thing. Alright. Now, in proving, instead of proving this, what I am going to prove it, if X and Y are at same potential, then this ratio will hold true. This equality will hold true. Okay? If X and Y, see, if this is true, then this is true for sure. And this also means that if this is true, this has to be true. If this is true, this has to be true. So I am going to prove it reverse. I am going to assume that X and Y are at same potential. Then finally, if I am going to get this expression, if I get this, that means our proof is correct. Okay? Let this is X, this is Y. Not let X and Y are at same potential. Alright. Now, from here, let's say this is point A. Let's say the potential here is VA. This is point B. The potential here is VB. Okay. Here, okay. Instead of VB, let's say here there is potential 0. See here. Let me make it more easy. We should not be having so much variables. This is potential V. The battery is providing. So there is no need of taking VA, VB. We can directly take this side is at higher potential, that is V. This is at lower potential, that is 0. So from here till here, no other resistance, nothing is there. It's a plain wire. So the same potential will be here, V. The same potential will be here, 0. No potential drop is happening. Okay. So this is at V, this is at 0. This is at some potential. This is also at the same potential which this is. Let's take this potential as V dash. Okay, let us take this potential at V dash as V dash. This is also at V dash. Make it a bit small. Now, for this, now we know if current I is coming from here. Here it will go I1, here it will go I2. And since we have assumed that this and this are at same potential, the same current I1 will be going here, the same current I2 will be going here. No current is going here. Alright. Now, from here if I want to write the equation of potential difference, what I can write is V. Potential difference across this resistor will be V minus V dash. Potential difference across this resistor. This point is at potential V. This point is at potential V dash. So V minus V dash is equal to V is equal to IR. Delta V is equal to IR, right? This is delta V. IR means I1 R1. I1 current is going here. Okay. For this, if I want to write V dash minus 0. This point is at V dash, this point is at 0. So V dash minus 0 means V dash only. Or let me write I1 R2. For this, if I want to write V minus V dash, again, this point is at V, this point is at V dash, is equal to I2 R3. Delta V is equal to IR. And this point is at V dash, this point is at 0. So V dash minus 0 will be I2 R4. V dash minus 0 is equal to I2 R4. Are yes or no? Now from here, see, let's say this is equation 1, this is equation 2, this is equation 3, and this is equation 4. Equation 1 and equation 3 are okay. If I divide equation 1 by 3, what I'll get? Or instead of dividing, equation 1 is equal to equation 3. See here, this is also V minus V dash, this is also V minus V dash. So from equation 1 and 3, we can write I1 R1 is equal to I2 R3. Okay, from equation 1 and 3, I1 R1 is equal to I2 R3. Here, I1 R1 is equal to I2 R3. So from here I can write I2 by I1 is equal to I2 by I1 is equal to R1 by R3. See, correct? From this I have got this. Now from equation 2 and 4, see, this is V dash minus 0, this is also V dash minus 0. So both are same. I2 R2 is equal to I2 R4. I1 R2 is equal to I2 R4. So from equation 2 and 4, I1 R2 is equal to I2 R4. Correct? Again, if I take I2 by I1, here I2 by I1 is there, so I am going to take that only. I2 by I1 is equal to R2 by R4. Now see, if I consider this as equation 5 and this is equation 6, from equation 5 and 6, can you tell me what is equation 5 and equation 6 telling? This is I2 by I1, this is also I2 by I1, that means R1 by R3 is equal to R2 by R4. R1 by R3 is equal to R2 by R4. Hence, proved. Are yes or no? What I told you here, if R1 by R3 is equal to R2 by R4, X and Y are at same potential. And this is known as balanced Wheatstone bridge. Now we have proved taking X and Y at same potential, X and Y are at same potential, then assuming what we got, R1 by R3 is equal to R2 by R4. Clear? So I hope you got to know. If this is the scene, always whenever you get any question like this, always see the ratio, the first thing. If the ratio is equal, remove this wire, solve the question, it will be very easy. Alright. Let's see one question. Now you have to tell me the equivalent resistance for this. Okay, find the equivalent resistance in the following circuit. How do we do this? So if you didn't know Wheatstone bridge, it was difficult to solve. But now you know Wheatstone bridge. What we'll do first, we'll see whether the ratio of this resistance and this resistance is equal to the ratio of this resistance and this resistance. Is it equal? Just check. 2 by 6, how much is it? 2 by 6, that is 2 1s are, 2 3s are, that is equal to 1 by 3. and 8 by 24. 8 ones are 8 threes are, that is equal to 1 by 3. That means this ratio is equal to this. See, both are 1 by 3. That means we can, this point and this point are at same potential. I can remove this wire. If I remove this wire, my equivalent circuit will be this is A, this is B, this is 2 ohm, this is 8 ohm, this is 6 ohm, this is 24 ohm. Correct? Now see, these two are in series. These two are in series. Easy to solve. 8 plus 2, 10. 24 plus 6, 30. So my circuit will be, this is 10 ohm, this is 30 ohm. A, B. These two are in parallel. R equivalent is equal, 1 upon R equivalent is equal to 1 upon 10 plus 1 upon 30. That will be 33 plus 1, that is equal to 4 by 30. Correct? 30, 10 3s are 33 plus 1, 4. So here R equivalent is equal to 30 by 4, that is equal to 7.25 ohm. See? 4 sevens are 28, 20, 7.5. 7.5 ohm. That is the equivalent resistance. Clear? Easy question. So from now on, whenever you see any question, try to recognize the kind of circuit it is. Okay? I hope you understood Wheatstone. That was the only new thing what we studied today. Right? In the next session, we will be seeing combination of resistors part 2, where a lot more complex and symmetric circuits will be there. Very interesting it will be. Okay, just revise these basics. Your basics should be strong for going into this particular session. The session what we did today was purely for boards. But what we are going to do next time, it is mixed boards and competition. Okay, very good questions can be formed from those. We'll be learning new tricks and techniques to solve the equivalent resistance thing. Okay, to solve the combination of resistances. Clear? I hope you liked today's session. If you liked it, do press the like button. Share it with your other friends who are preparing for their competition and boards as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Alright? Do not forget to visit our website also, www.v-learning.in. In that website, you will be getting all these sessions what we are providing here. Along with that, you will be getting lecture notes also for each and every lecture in PDF format. You can go download it, read it from there, learn it from there. Okay, it will be very useful for you. Go do check it out. Fine. We'll meet up in the next session. Till then, keep learning from V Learning. All the best.